So this is a very simple case. What we are taking here, Mohr circle for stresses on oblique plane of a body subjected to direct stress in one plane. Right? There is only one simple stress applied along x direction here, and I have to find the normal stress and shear stress on the oblique plane AB, right? Now for this, first I have to construct the Mohr circle diagram, right? So how to construct, let us see. Now I have this stress value sigma, so I have to see the magnitude of the stress, and based on that I will choose a suitable scale, right? Now after choosing a suitable scale, what we have to do is first draw a horizontal line xx. Now on this, uh, whatever scale we have chosen, based on that you convert it into sigma, the required length, and mark OJ, which is representing your normal stress sigma, and then you bisect this line, you will get the center, and using that you draw a circle. I have bisected, so I got the center, and then I have drawn a circle using that as the center. So this circle is drawn based on the stress. That is why this is called as Mohr's circle of stress, right? It is developed by a scientist or engineer named Morse. That's why it is called Mohr's circle diagram. Now what you have to do is, you know the inclination theta here, so draw a line CP such that the inclination with respect to x axis is 2 theta, because in my equations I have used 2 theta, so I am drawing a line which is inclined at 2 theta. So if the theta is given as 45 degree, it will be 90 degree. Whatever angle is given, you just have to multiply it with 2. Then you draw a perpendicular from P to the x-axis, that is PQ, and then you join OP, right? So now in this diagram, OQ, this length, is representing my normal stress sigma n. Now how to find OQ? We have OC equal to CJ is equal to CP, right? They are all the radius of this circle. The diameter of this circle is sigma, so the radius of the circle will be sigma by 2. So OC, CJ or CP, all these three are equal to sigma by 2. Now OQ, that is this length, is OC minus CQ, right? So OC is sigma by 2 and CQ is CP cos 2 theta. CP is again sigma by 2. So sigma by 2 minus sigma by 2 cos 2 theta, or it will be sigma by 2 into 1 minus cos 2 theta. So if you go back and see the expression, it is the same expression that we had got analytically, right? So we obtained this equation very simply by drawing this diagram. Now in your solution, you don't have to use these equations, you just have to draw the circle. So just measure OQ from your Mohr circle diagram. That will give you the normal stress on the inclined plane. Then the line QP, this vertical line, is giving the shear stress, that is tau. So you have to measure this QP. QP is also CP sine 2 theta. This is the opposite side, and CP is sigma by 2. So QP is equal to sigma by 2 sine 2 theta. So I am getting the same expression. This is only for our proof that analytical method and graphical method will give you same result. So what you have to do now, let us say I have taken 10 megapascal is equal to 1 centimeter or something like that as the scale. Then you have to just measure this length and multiply by the scaling factor. That will give you the shear stress and normal stress on the inclined plane, right? Now for maximum shear stress from this equation, sine 2 theta, when this is maximum, you will have the maximum shear stress. So that is possible when sine theta is equal to 1 or 270, right? These are the two values. So 2 theta is 90 or 270, or theta is equal to 45 degree or 135 degree. Along this plane, you will have the maximum shear stress. Okay, so this is a very simple case. Now next we will see the stresses in two perpendicular directions. Okay, there is one more thing, that is the resultant stresses OP. This will represent the resultant stress OP. Now Mohr's circle for stresses on oblique plane of a body subjected to direct stress in two mutually perpendicular directions. So here I have sigma x and sigma y, both are present, right? There is no tau still. When tau comes, then this becomes slightly complex. We'll see that in the next class. Today we will only solve these two type of numericals. So here what you have to do is, the construction is more or less same. On the x-axis, first I have drawn sigma x and sigma y with O as origin. So OK represents sigma y, OJ represents sigma x, right? Now I get 2 points K and J. So first you have to bisect these 2 points. So by bisecting, I get the midpoint of KJ at C. Now with C as center and CK or CJ as radius, you draw a circle. So this is your Mohr's circle now. Now from C, you draw a line inclined at 2 theta, right? This is theta. So this is 2 times theta. Please don't go by this diagram, because you must be wondering, theta is also inclination, same giving same inclination. Here also you have same inclination. This is only for indication. So with respect to this, if you take 2 theta, it will be something like this, right? This point may shift somewhere here. Whatever angle you get, you just measure. One thing you need to keep remember in mind is, the angle is measured in clockwise direction along the x-axis. So from here you have to measure in clockwise direction. So you get QP, then you drop a perpendicular PQ, and then you join P and O. Now OQ gives you the normal stress sigma n, PQ gives you the shear stress, that is tau, and OP gives you the resultant stress, right? So now let us try to verify this. OQ is equal to normal stress, that is from here to here. So from this diagram, I can say KC is equal to CJ is equal to CP is equal to sigma x minus sigma y, right? This minus this by 2, right? Half of that. That is the radius of the circle. Excuse me. Now OC, right? OC from here to here is equal to OK plus KC, right? So OK is sigma y and Kc is sigma x minus sigma y by 2. So just multiply this by 2 and put it in this numerator. So it becomes 2 times sigma y plus sigma x minus sigma y, or it is sigma x plus sigma y by 2. That is OC here. Now I can calculate OQ. So OQ is equal to OC minus CQ. OC is sigma x plus sigma y by 2 and CQ is CP cos 2 theta. CP is sigma x minus sigma y by 2. So if you go back and see, this is the same expression what we derived for this analytical. Now QP, that is this vertical line, is representing the shear stress. So QP is equal to CP sine 2 theta, right? So this is hypotenuse CP and that value is sigma x minus sigma y by 2 sine 2 theta. Again here also shear stress is maximum when sine 2 theta is equal to 1 or minus 1. So that is possible when theta is equal to 2 theta is 90 degree or 270 degree, or theta is 45 degree or 135 degree, right? So that's how you get, and the resultant stress is OP, right? OP is the resultant stress.